Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for students going through integral calculus and integration techniques. What we're doing in this video is a single example that illustrates kind of an edge case when it comes to integration techniques. I've listed out some of the most popular integration techniques that we've probably learned up to this point. You should already know direct integration, obviously, because if you don't, well, you're not in Calc 2. You should also know basic or standard U substitution because you learned that in Calc 1. And then you learn new techniques like forcing even powers on trig functions. That's always very powerful. And by the way, I never really mention it in my videos, but when I say forcing even powers on trig functions, there is one exception, technically two, and that's when you have the products of secants and tangents or cosecants and cotangents. There is a case where odd powers are perfectly fine, but I usually leave that for students to self-discover. Another kind of specialized substitution are trig subs, which are basically what you're going to use if you have a sum or a difference of squares. Not always. A basic U sub is very powerful at times when you have a sum or a difference of squares. For example, something like this right here, I definitely would not use a trig sub on. I would just let u equal x squared plus 4 so that du would steal away that numerator and I would totally finish out that integral from there. So don't just think, well, if I have a sum or difference of squares, I'm always going to use trig subs. That's not the case. And then there's a new type of substitution called a radical substitution that I will focus on in this video. Beyond those specialized substitutions, we also have integration by parts and then partial fraction decomposition, which could be listed as another name in your textbook, possibly like integrating rational functions using decomposition or something like that, but most people call it PFD, for partial fraction decomposition. And as a heads up, you can only use partial fraction decomposition if you have a ratio of polynomials. So please do not try to use it on a ratio involving anything but polynomials. Now back to the problem at hand. We are asked to integrate, using a definite integral from 4 to 11, the ratio of non-polynomials. The numerator is definitely a polynomial, but the denominator is not. So do not use partial fraction decomposition. I'm actually going to go ahead and cross that out right now. Obviously, you can't use direct integration. There's no trig functions here, so forcing even powers on trig functions is out. I don't see a sum or a difference of squares, so that's out. It's not really a product of two different kinds of functions. Yes, technically it is a polynomial times 1 over a radical, but I kind of feel like polynomials and radicals are the same family of functions, and so by parts is a little bit out. Now you can see that only leaves us with two techniques, standard U sub or a radical substitution, and I'd actually like to try both here. So let's pretend as though you decide I'm just going to use a standard U sub. I would not blame you. I think that this is very attractive for a standard U sub. So you say I'm going to let u equal x minus 3 so that du will steal away a regular old dx. Well, because that numerator is not just a regular old x or anything like that, I should rewrite it in terms of u. Adding 3 to both sides of our substituted equation there, we will get u plus 3 can be traded in wherever we see an x. And it turns out this substitution is a pretty darn good substitution. There's no need to use an advanced technique here. And you'll find this happens more and more as you move up in calculus, is that you're introduced to high-level techniques and all of a sudden somebody throws an integral at you that doesn't require any of those high-level techniques. It just requires basic U substitutions. So always keep an eye out for that. The last thing I'm going to do is trade out these limits of integration. If x is equal to 4, then u is equal to 1. And if x is equal to 11, well then, u is equal to 8. Let's go ahead and perform all of those substitutions. Remember, the x in the numerator, I'm going to trade out for a u plus 3. We have the cube root of x minus 3, but x minus 3 is going to be u. And I dislike writing cube roots in calculus, so I'll write that as u to the 1/3. And finally, dx gets traded out for a du. This is a wonderful problem because it can be done this way. Cleaning up the numerator, remember, always go back and try to do arithmetic and all that stuff before calculus. And as a reminder, do some arithmetic or algebra before you do your calculus. I can break this fraction up into 2 fractions and use laws of exponents to rewrite everything. And we arrive at this beautiful integral that is actually pretty easy for us to do. These are just the simplest form of integration where we add 1 to the exponent, divide by the new exponent. Or another way to say that, add 1 to those exponents and multiply the coefficients by the reciprocal of those exponents. That's what I'm going to do here. And we'll evaluate those from 1 to 8. And I already pre-computed the cube root of 8 there to be 2. Now let's go ahead and finish this out. A lot of people wonder why I don't actually multiply out, for example, the 32 times the 3, or why I don't cancel, for example, this 2 with this 2 in the denominator. There's a very cool trick you can use here. Notice I have 32 sets of 3/5 here, minus 1 set of 3/5 there. Altogether, I have 31 sets of 3/5 left over. That's why I do that, is because I just want to see kind of what combinations of things I have. Just like over here, I have 4 sets of 15 halves and I'm losing 1 set of 15 halves there. So 4 of them minus 1 of them, I'll have 3 sets of 15 halves left over. And now I will actually clean this up. So unless I made any arithmetic mistakes, that should be 411 over 10. Now, I really don't care about the arithmetic there, actually. What I care about is that you can get to this point and find the antiderivative and possibly just substitute it and stop. But anyhow, why did I do that in this video after we have gone through all of these methods? All I did there was use standard U substitution. Well, the reason why I did this example here is because I want to showcase or introduce you to a brand new type of substitution that can be incredibly helpful. I'm not going to say it's going to speed up things too much, but it will speed up a little bit. So let's take a look at, again, this integral, but instead of doing the U substitution that I performed before, I'm going to let U equal that entire radical in the denominator. So if U is equal to the cubed root of x minus 3, then what you can do is you can do a little bit of algebra before you start into your calculus. Just cube both sides. Now looking back at the integral, we will have replaced this denominator here with u. We still need to replace that x plus 2 in the numerator, so let's go ahead and figure out what x plus 2 is. I'll just go ahead and add 3 to both sides of this. Now we know that x plus 2 will be, well, u cubed plus 3 plus 2. We also need to find out what dx is, and that's what's nice about cubing both sides first. If you take the derivative of both sides now, you get 3u squared, and then the differential du is equal to the derivative of the right-hand side, which is 1, times dx. So we immediately know what dx trades out for as well. So we have all of this stuff really that we know. Now let's just trade out those limits of integration. If x is 4, just looking at this right here, we'll have the cube root of 1, or in other words, u is just 1. If x is 11, we'll have the cube root of 11 minus 3, or the cube root of 8, which is 2. And our integral becomes the integral from u is equal to 1 to u is equal to 2. Remember, the numerator is x plus 2, but again, x is going to be u cubed plus 3. Add 2 to that, it's u cubed plus 5. our denominator, which was the cubed root of x minus 3, well, that was just u. And then finally, the dx gets traded out for a 3u squared du. I'll put the 3 out front, and we get to here. This u obviously cancels with the power of u here. And I distributed that remaining power of u through the numerator in the fraction. And note that this integral is actually a lot easier to deal with. Substituting in, we get to this point right here, and I promise you that it's actually the same value as what we got up here. I'm not going to work it out. It just is the same value, I promise. So this is an introduction to what we call a radical substitution. It is always an option if you have an integrand involving a square root, a cube root, a fourth root, or something like that. You could let u be that entire radical and then just raise both sides to whatever index the radical is. So if it was a cube root, we raise both sides to the third power, and that cleans that up so we don't have to take derivatives of radicals. Instead, we have just nice polynomial terms. So again, this example illustrates not a brand new method, just a new idea. We already knew how to do a u substitution, but often we were told, well, let u equal the x minus 3. But now I'm telling you, you could always allow your u to equal the actual radical. But when you do that, make sure that you end up raising both sides of that resultant equation to, in this case, the third power, or basically the power of the index. And that'll get rid of all radicals and then work from there. All right, I hope this example sheds some light on a new tactic. It's not actually a new technique, but a new tactic that will be very helpful as you move forward in calculus. I hope you have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.